China's bold announcement of a next-generation photon detector has ignited global discussion. This device is presented as sensitive enough to register signals too faint for conventional systems, sparking speculation about its impact on advanced sensing. Yet experts say the real story lies between promise and proof. In this video, we examine what China claims, what specialists believe is technically realistic, and why this technology raises big questions about the future of detection. Band radar has been promoted in recent years as a technology capable of seeing what traditional radar systems miss, especially aircraft designed to reduce their visibility. In media narratives, band radar is framed almost like a spotlight in a dark room, a sensor that reveals the true shape of objects that normally blend into the background. This hype reached its peak when claims suggested it could spot advanced low-visibility aircraft such as the F-22 and B-2, implying a major shift in how detection might work in the future. To understand why these claims gain traction, it helps to revisit one key radar principle. Different frequency bands interact with objects in different ways. Higher frequency radar provides fine detail, but is more easily scattered or absorbed by specialized materials and angled surfaces. Lower frequency radar interacts with aircraft differently. It isn't as easily minimized by shaping alone, which is why some analysts find band radar intriguing. Its longer wavelengths aren't affected as dramatically by designs intended to reduce reflections. This theoretical advantage is what originally led to bold statements about band radar opening a new era of detection. Supporters argue that it might bypass some techniques used by low-visibility aircraft designers, offering a new path for locating objects with subtle radar signatures. Combined with algorithmic filtering and sophisticated arrays, the idea sounded transformative. However, the promise behind this technology often overshadowed important limitations. Lower frequency radar tends to have poorer resolution, meaning it can detect that something is present but struggles to determine what it is or track it precisely. This makes the technology interesting as a supplementary tool rather than a complete detection solution. Without a clear demonstration of accuracy, range performance, clutter management, or stability in real environments, the boldest versions of these claims remain unproven. The appeal of band radar comes from its potential, not its confirmed capability. Its longer wavelengths interact with objects differently than conventional systems, but translating this basic interaction into reliable, high-confidence detection is far more complex than headlines suggest. The story is less about a breakthrough and more about a technology that sits at the intersection of physics, engineering challenges, and public imagination. While band radar was promoted as a near-revolutionary tool, experts quickly pointed out the difference between theoretical sensitivity and operational performance. Specialists in electromagnetics emphasized that detecting low-visibility aircraft requires far more than a radar band with favorable interaction properties. It requires stability, precision, environmental control, and advanced signal processing, none of which appeared in the claims being circulated. This gap between promise and proof is the foundation of the skepticism surrounding the technology. Engineers highlight several critical shortcomings. First, lower frequency radar inherently suffers from resolution limitations. Even if it detects a presence, the return might be so broad or vague that it cannot reliably classify what the object is. A faint return does not necessarily equal actionable detection. For modern sensing, the ability to differentiate between a cloud, a bird, and an aircraft is essential, and that requires finely tuned resolution, not just wavelength advantage. Another challenge comes from environmental clutter. Longer wavelengths interact strongly with terrain, weather, and atmospheric variations. These interactions generate noise that complicates interpretation. The more sensitive a radar system becomes, the more interference it must filter out. Without proof of advanced algorithms or hardware stabilization, any claim of high-confidence detection becomes difficult to accept. The debate took a dramatic turn when a Zhihu user, reportedly a radar engineer, claimed that the research papers cited to support band radar's effectiveness were based on a bare metal model of the B-2. The post gained over 1,600 upvotes and quickly spread across discussion circles. The allegation suggested that for nearly a decade, simulations portraying band radar as capable of detecting the B-2 did not use a realistic representation of its actual low-visibility features. Instead of modeling the aircraft with its specialized coatings, edges, and signature management treatments, the papers allegedly used a simplified metal shape. This distinction is not minor. A bare metal aircraft reflects electromagnetic waves far more strongly than a real low-visibility platform. Using such a model can dramatically exaggerate how effective a radar system appears in simulation. If true, this would mean the theoretical work behind the band radar claims was built on conditions that do not resemble real-world physics. However, it is important to state clearly, this Zhihu claim is unverified. No academic paper has been publicly corrected, no institution has acknowledged an error, and no independent experts have confirmed the allegation. The story's spread demonstrates how quickly online discussions can influence public perception when technical transparency is limited. The allegation resonates because it highlights a broader issue: the lack of publicly available testing data. If a technology is presented as a major advancement, yet supported mainly by simulation, people naturally scrutinize the assumptions behind those simulations. The Zhihu post feeds into that scrutiny, raising the question of how much confidence can be placed in research that does not disclose its full modeling parameters. This episode also shows how nuanced the topic is. Even without the allegation, relying heavily on simulations creates uncertainty. A simulation is only as accurate as the model it is built on. Without clarity about model fidelity, geometry, materials, and environmental conditions, external observers have little way to assess reliability. The conversation sparked by this post ultimately reflects deeper concerns. Bold claims require bold evidence. When evidence remains inaccessible, interpretations fracture, leading to a mixture of enthusiasm, skepticism, and speculation. Regardless of whether the Zhihu allegation is true, it underscores the need for transparent validation before any technology can be considered a confirmed breakthrough. The discussion around band radar shows how easily bold ideas can outpace confirmed results. The technology has intriguing theoretical strengths, but the evidence supporting its real-world effectiveness remains limited and often unclear. Expert analysis, environmental challenges, and the unverified Zhihu allegation all highlight the same point. Meaningful breakthroughs require transparent validation. Band radar may eventually play a role in future sensing systems, but today it remains a developing concept rather than a proven capability. Understanding this gap helps keep expectations grounded as the technology continues to evolve and invites continued curiosity about where sensing innovations may lead next. If this video opened new ideas for you, tap like, share it with someone curious, and subscribe for more insights. Thank you for watching and supporting the channel. Your engagement helps us explore even bigger topics together. See you next time.